Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Noriaki Nakayamada from NuFlare, who's going to talk today about how to speed up the mask process with GPU acceleration. Noriaki, what are you seeing as some of the main problems in the photomask shop these days?
Okay, let me start from the explanation of the physics of electron beam lithography.
You want to draw this out for us?
Yes,
So what are we looking at here?
yes, we are making electron beam mask writer, and our mask writer uses 50 kV electrons, and 50 kV electrons hit the resist to make photomask patterns. But when the electron hits the substrate, most of the energy, initial energy, 50 kV, is converted to heat. And as soon as the heat is generated, it starts to diffuse or dissipate. But writing continues from this shot to this shot and this shot. But this speed of writing, if it's not fast enough to escape from the heat diffusion, it is caught by the wave of the heat, so that the temperature of this shot gets higher than the previous shot, and the latter the shot becomes, the higher the temperature be. And
What sort of problems does this cause when you start getting that kind of heat buildup?
yes, so as the nature of resist, it has higher sensitivity to electrons at higher temperature. And higher sensitivity means that the size or the CD, critical dimension of the pattern, is affected by the temperature to have, in this case, bigger size.
Is that just a function of normal expansion?
Yes, it's basically a linear correlation between temperature and the size of the pattern.
So how do you solve that?
Yes, to solve it, you have to calculate the temperature at the time that shot is written. And to do this, you have to calculate the heat transfer from all the shots written previously. For example, when the first shot is written, the temperature rises 0. But for the second shot, it gets heat transfer from the previously written shot, which is first shot. And the third shot, gets heat transfer from the first one and also the second one. And so the total calculation of the heat transfer will be 1 plus 2 plus 3 plus blah blah blah, total n shot, which corresponds to n times n plus 1 divided by 2, which is essentially proportional to square of the n. N means the number of shots. So the calculation cost is proportional to the square of shot count, while the writing time is essentially proportional to the number of shots. So the gap between writing time and calculation time diverge as the number of shots increases.
So one of the problems that we're running into is throughput on the masks, right?
Yes.
And so this is geared toward, if you spread the stuff out, you're going to have less of an issue with thermal problems, but the problem is you lose your productivity inside the mask shop.
Right. What we are doing in the past to mitigate or reduce this heating effect was to increase the pass count from 2 pass to 4 pass, and sometimes even more aggressively for 8 pass for a nano imprint application. But yes, you're right, it has a throughput impact. And what is desirable is to correct the heating effect by the software and hardware.
Does this cause any mask warpage? Is that a problem because of thermal issues?
Yes, the critical dimension error is increased to maximum 4 nanometer without any solution given. But we want some number close to 1 nanometer as a whole product accuracy, photomask product. So we got to do something to reduce the CD error to the required specification.
At what node does this start becoming a problem?
Yes, this has been an issue for a long time, but we could manage to mitigate it by, like I said, increased pass count and also boundary shifting writing technology did help in mitigating this impact. But from 7 nanometer node, which is supported by EVM 9500, the effect is no longer negligible. So we have released this solution starting from this EVM 9500.
And that's been a recurring theme as we start moving down into the single-digit nanometer nodes, right? It's what's your critical dimension? How much can you see? Is the equipment there for measuring this stuff properly? We've got issues on every side, from the mask all the way into the silicon manufacturing.
Yes. Right now, we are testing the correction efficiency with a lot bigger size. I mean, the test vehicle has about several hundred nanometer pattern. To clearly detect the improvement, we need to have bigger pattern size to avoid any other effects affecting the smaller pattern sizes. So, but that's our next step, to test it with smaller features. How resist heating effect is impacting smaller features. That's our next task.
Does the lithography source matter at all here? Are there multiple options?
That's one thing we have to test in future. We are testing ARF masks now, and we don't have much data with EUV mask yet. But that's a good point. The EUV mask has thick metal layer compared to ARF mask, so the heat dissipation, diffusion coefficient may be different from that of ARF mask. So that's one thing interested in testing in future.
So where do GPUs fit into this, and how do they affect what you're doing?
Yes, to calculate the temperature for each shot, you have to calculate or accumulate the heat transfer from the previously written shots. And the total cost of calculation is written down below: 1 plus 2 plus 3 plus n equals n times n plus 1 divided by 2, which is essentially proportional to square of shot count. And on the other hand, the write time is proportional to the number of shot counts. So the gap between write time and calculation time diverges as the number of shots increases. GPU works perfectly to make calculation time closer to write time to fill this gap.
Basically, what you're doing is solving the problem with hardware and throwing a lot of cycles at it, right?
Yes. We are working with D2S company. They provide pretty well designed, established computational platform, which they call CDP, and which has about several tens of servers equipped with several hundred GPUs.
So you're raising the abstraction level, and you're also cranking up the number of cycles that can be done per second.
That's right.
Okay. So when you get all this done, what does this do in terms of, are we still staying current with, as we move down from one node to the next and one mask problem to the next, are we still able to maintain a consistent amount of time that it's going to take, or are we falling backward?
That's a good question. The entire life of VSB, single beam technologies, is already ending, and we are making next platform using multi-beam systems. And multi-beam system, we handle pixel data instead of shot data, which is essentially rectangle data. And GPU perfectly fits that purpose of pixel data handling, because pixel data is essentially graphics data, and the G from GPU comes from graphics, so it works perfectly.
What's the time frame for introduction here on this technology?
Yes, we are planning to release it from Q4 or end of next year, 2017.
So a mask shop is 24/7. As you add a GPU type of approach into there, lots more cycles running very quickly. What does that do to reliability? Is there an impact?
Yes, I cannot say there is no impact. There is an impact of having GPU in such 24/7 required environment. But D2S already has solution by carefully designing and implementing software with very sophisticated redundant and recovery system, so that any single failure of GPU does not result in yield loss or the photomask loss.
Noriaki Nakayamada, thank you very much for a great explanation of a very complex subject.
Thank you very much.